Hi, and welcome back. So on the next episode of Sensation and Perception, we have this topic, ecological psychology and/or the ecological approach to perception. What in the world is that, right? Why are we talking about ecological psychology in a perception class? Well, believe it or not, I think that the study of perception is at the heart of ecological psychology. In fact, one of the primary names in ecological psychology is J.J. Gibson, who gave us the title here, Ecological Approach to Perception. This is really a continuation of two things we've talked about previously. So if you refer back to the very end of the first topic, sensation and perception, the last slide there, I presented the ecological approach as an alternative to the sensation-mediated view. And one of the things that I did was kind of referring to there. I didn't provide very much detail about what exactly the ecological approach is, but I was presenting it mainly as a contrast, right? So the idea is with the sensation-mediated approach, we have to bring in all of these meaningless or ambiguous sensations, and there's a lot of sort of internal cognitive work, processing, inference, what have you, that has to be done to fix up those sensations, to turn it into a meaningful perception. And I also equated this with what we have also called a poverty of stimulus assumption, which is that the stimulus for vision is inherently impoverished, meaning it's poor and weak and really cannot inform us about what's happening in the world. And that requires us to have a lot of internal work to figure out what it must mean. This came up again in the third topic, which was the problem of constancy, because I revisited the poverty of stimulus assumption in the constancy notes when talking about this idea again that it is difficult to explain how retinal images or visual sensations can specify what's actually happening in the world around us. And if the visual input cannot tell us what's happening in the world around us, then that raises the whole question, well, how in the world do we know what's happening in the world around us? Without, of course, the idea that there has to be some, again, a lot of cognitive work happening to interpret and decode the sensations. But the alternative that I previewed in the sensation and perception note was that maybe we could have a theory that does provide information in the visual stimulus, right? As opposed to treating it as impoverished. And so we're going to call that here an information-driven approach as opposed to a sensation-mediated approach. And at the end of the constancy notes, we talked about this in the form of the so-called perturbation experiment. But in that setup to the perturbation experiment, I was talking about the idea of this mapping issue, right? And one of the reasons why visual sensations and retinal images are treated as ambiguous as they are is because of the many-to-many mapping problem. And what we would really hope to see is a one-to-one mapping, right? The idea is that if we can discover a one-to-one mapping between a particular state of affairs in the world and a particular visual input, then that's not ambiguous, right? That would eliminate the ambiguity that's causing this problem in the first place. And if we can do that, that means we can possibly abandon the poverty of stimulus claim, and we can show that there's information available to the visual system. Now, so far, I have only just hinted at this approach, right? And I think I said this when talking about this at the end of the constancy notes, that what we still need to do is one thing to assert that we might find such patterns in the light, right? The idea is we talked about light reflecting from objects and events, and that there might be patterns in these lights. And I talked about it in a small amount of detail with the progressive occlusion example and a little more detail with the moving room experiments as an example of a perturbation experiment. But here, I want to actually get into the real meat and potatoes of how we can discover information that could be available to a visual system, right? And how we can scientifically justify the ecological approach. So let's have a look. Well, I guess I probably could have went to this slide uh, already. This is simply just summarizing what I just said about and reviewing what we previously covered about the problem of constancy. That because of that many-to-many mapping problem, retinal images and visual sensations have been treated as ambiguous and unable to inform about the state of affairs of what's happening in the world, unless, of course, we have some sort of internal cognitive processing to fix it up. But our new idea that's going to be the basis of an ecological theory or direct perception theory is that we're going to reject the claim that perception is based on sensations, and we're going to replace sensations with something else. And that something else will be information. And that information will then be hypothesized to have a one-to-one relationship. And that one-to-one meaning unique relationship, as in not ambiguous relationship between itself, the information itself, and something happening in the world. And this stems from, as I had mentioned, the work of J.J. Gibson. So Gibson's approach is called the ecological approach. Why is it called the ecological approach? Well, I don't think we want to spend too much time on that little point, but just to address that in case it bugs you, if you have any questions as to why we're calling it this. Gibson's claim is that when we think of an animal's ecological niche, we usually think of the physical features of the environment, right? We think about the fact that animals evolve the ability to walk upright because of the physical features of the environment, including a particular level terrestrial ground plane as well as gravity, right? Or that we evolve, mammals, warm-blooded mammals, because of the oxygenation and warmth of the environment, right? Well, that, of course, is all true and relevant to evolution, but what's also potentially, and this is where Gibson comes in here, true and relevant to evolution, is the presence of light, right? And the idea is that the light here is not simply just the kind of electromagnetic radiation that is discussed when we talk about the visible spectrum of light, ranging from 400 to 700 nanometers and all that. But there is something that happens, and we're going to get into these details shortly, when light reflects from surfaces in the environment. And this reflected light is part of an animal's environment. And if this reflected light has patterns and meaning in it, then that means that all of that is part of our ecological niche. And therefore, we want to think about visual systems as having evolved inside of this information-rich environment. So the important claim to be made here is that information is found in the environment. And the goal of evolution here is to evolve visual systems capable of detecting and extracting that information from the environment. You see the important distinction here from the classical sensation-mediated view is that in the sensation-mediated view, information is found only inside the brain or mind of the perceiving animal, right? The input coming in is meaningless, and meaning has to be imposed on it internally. This, by the way, is a very old way of thinking about knowledge and perception, which has its roots in classical mind-body dualism, right? The outside world is just, there's no meaning to be found in the world. Meaning is only found in the mind, right? This is consistent with Kantian ways of thinking about the mind, or even Cartesian ways of thinking about the mind. And Gibson's view is very different from that, because he's claiming that there is information and therefore meaning to be found in the world. And what we need is a visual system or any kind of sensory system that can extract and detect that meaning. So of course, Gibson tends to work within vision. He was trained as a vision researcher after all. But we could extend the concept to any of the other senses as well, right? And we could suggest that there are meaningful patterns in the sound pressure waves, and that auditory systems evolved to detect and extract information from that, and so on and so forth for all of our senses. But we're going to keep this within the realm of vision because that's the origin of this theory, and that's where most of the work has been done, and that's where a lot of nicely detailed studies have been performed to work out the exact patterns that can be present and study that. So that's where we're going to keep the focus here. So informative patterns in structured light arriving at the point of observation. That's the source of information for vision at this point, right? We're going to talk about light arriving at a point of observation, but the important thing to say here is that the patterns in the light are defined external to the eye. It's in the world, right? It's part of the ecological niche here, right? And this is why when we talk about this, we talk about a point of observation. So what in the world is that? Well, a point of observation is any point in space where we might place an observer. And saying an observer is really just another way of saying that any animal that has a visual system can be an observer, right? And so we're going to talk about light reflecting from surfaces that contain patterns. These patterns can be thought to be informative, and calling it structured light is just another way of talking about patterns, right? The idea is that any kind of a structure in a light, ambient light would simply just be a pattern, right? And the point is that these patterns are informative about some state of affairs in the world. So that means we're going to sort of, as I note here in the bottom, the idea is that all of that stuff about proximal versus distal stimulus is no longer part of this theory. Sensations are no longer part of the theory, and therefore having to process sensations into perception and worrying about what's the difference between sensation and perception. Those kinds of questions are not really found within Gibson's approach here. The idea is much more simple and direct, which is that there's something happening in the world. That world is also illuminated with light, and that light is a medium that transmits or carries information. And then visual systems within this world can detect that information. And therefore, by detecting that information, they are perceiving what's happening in the world, right? It's just a direct process. No mediation, no translation, to refer back to the translator metaphor that I had mentioned in the past. Well, so what exactly is this pattern, ambient light, reflected light? This is called in Gibson's theory the optic array. And let's get into the detail here a little bit. So as I just said, we're going to treat light as a medium. What is that? A lot of times when we think about how we talk about visual sensations, we talk about the light rays having certain properties, right? And the idea is that, light can be described as having a certain number of photons, photon flux, as well as the wavelength, and that those are the properties that we perceive. And what that would suggest is that what we're perceiving is we're perceiving light itself, right? And we're perceiving the light in terms of its intensity and its wavelength. But the claim here is that we are not perceiving light or light rays or photons. We are perceiving via light, right? That means light is essentially a something that carries information. It is not itself the visual stimulus. That's an important point, right? Light is not itself the visual stimulus. Light is simply a transmitter of the information, and that information is the visual stimulus, and that information comes from the environment, right? Comes from objects and surfaces in the world around us. And so light transmits this information. It's a medium that carries information, just like radio waves, right? Think about it this way. Radio waves are a medium, right? And so when a radio antenna detects radio waves, it doesn't simply just detect the waves, it transmits the pattern embedded within the waves. And that pattern embedded within the waves can be a song broadcast by a radio station, right? And that's the what the information that is carried by the wave, right? And so the same now is true for light. We're going to treat information as being carried by the light patterns. And our job here for our visual system is to detect those patterns and vis-a-vis those patterns, perceive the world directly. So in order to maybe do this, we want to visualize a little bit. So what we're going to do here is we need to make a distinction between two kinds of light. It's all light really, but we can characterize light in these two ways and make a distinction between what we call radiant light and ambient light. So radiant light is, just as the name implies, it's radiation, it's electromagnetic radiation. And as I said, it can be described in terms of its photon flux as well as its wavelength. So this is the kind of light that we talk about as being emitted by a light source, right? So the reactions happening in the sun, that emits radiation, including, of course, the visible spectrum of light and photons. Light bulbs, the filament in a light bulb, same thing, right? It emits photons, and therefore it's emitting light in the visible spectrum. And that's radiation. It's electromagnetic radiation. That kind of radiation is what we would call unstructured, and synonymous with that is homogeneous, meaning there's no pattern. It is equal in all directions, right? It is the same in all directions. And that's what we're looking at here on the left, is we see a light bulb at the top of the room, and the filament in the light bulb is radiating light in a homogeneous way throughout the entire environment, which is a room with a table in it, right? And what we're also seeing here is all these little scatter points on the walls and the top of the table. That's what happens when light strikes those surfaces. So the light is traveling out in all directions from the light source, and it comes into contact with surfaces in the environment, and those surfaces will reflect light. There are different kinds of reflections, and we could get into a lot of details about that, but I don't think we really want to. But the idea is different kinds of surfaces, whether they're covered in cloth, like a matte surface like carpet, versus something that's more shiny like metal or glass, will reflect light in slightly different ways. Of course, it's important to keep that in mind, because what we're now suggesting is that it's this reflected light, which we now call ambient light, right? And the light, as it reflects from a surface, is going to now undergo a change, right? And as I suggested, matte surfaces or glossy surfaces will reflect light in slightly different ways. And what that means then is that this reflected light is now influenced by the nature of the surface that it has reflected off of. And so light reflecting from a glassy mirror or a window or a shiny metal piece of something will be very different than light reflected from a carpeted floor or a painted wall or any such thing, right? And so that's the idea here, is that all of these different kinds of surfaces that are made of different kinds of materials will interact with light in different ways, in ways that are in fact physically lawful, as it turns out, right? It only makes sense that an object that's made out of a certain substance and may contain certain chemicals or pigments, will absorb some of the wavelengths and reflect other wavelengths, and the way in which it reflects those wavelengths in terms of the angular deflection of the light depends on properties of the surface. And so what we're seeing on the left are these lines. We want to think of those as the light rays themselves, traveling in straight lines from the light source to the surfaces and then reflecting in many different directions. But on the right-hand side, we're trying to visualize now ambient light. And so now these lines are light that's not coming from the light bulb, but rather it's light that was the radiant light but now after having struck surfaces in the room are reflecting off of that. And so now this is ambient light. This is now the reflected light. And this reflected light goes all throughout the room, of course. But what's relevant to vision is what subset of that reflected light converges to a point of observation, right? So remember I said that before. So a point of observation can be defined as any point in the room that may be occupied by an observer. So in this case, we have a person seated in the chair, and we have all of those light rays, the solid lines, converging to where that person's eye is. And what we want to ask here is not what's happening inside the person's eye or brain, at least not yet. What we want to ask is what kind of pattern is present in those light rays, in those actual solid lines, reflecting from all the various visible surfaces in that room to that one point in space, the point of observation. And then something else to think about is that when our person stands, and so now we look at the dashed lines, they are changing their point of observation in the room, right? They move to a new location. And that means the pattern of light that's available at that point of observation is now slightly different than it was before. So they have moved the point of observation to a new point, and they have now transformed what we'll call the optic array. So the optic array is that bundle of all of these angles, right? These visual angles converging to the point of observation. And when seated, the observer is able to sample the optic array at that one point in space. And when standing, they have now sampled a different part of the optic array by transforming that. We note, of course, that there are some parts of the optic array at that point of observation that cannot be sampled because we don't have panoramic vision. So there are some light rays from the back of the room that are just converging to that point, but are intercepted by the person's head, right? And so our seated person cannot see the behind them, but in principle, these are all of the ambient light rays converging to that point. A portion of it is sampled by the visual system. That's ambient light, and that's the optic array. And this is what Gibson says is the real source of information and vision is the optic array, all of that reflected light converging to the point of observation. Here is another, and this is just for the sake of clarity and exposition here so that you understand. This is just another drawing depicting the same idea, right? The ambient optic array, ambient referring to the ambient light, is light reflecting from surfaces in the environment and converging to a point of observation. So here again, we see a seated observer in image A, who can see a table and a lamp and a portion of the wall, and looking out a window can see a portion of a car. All of the solid lines are visible parts of the scene, and all of the dashed lines are parts of the scene that would not be visible from that particular position, right, from that particular point of observation. But when the person stands up, that changes the point of observation. Different parts of the scene come into view. Some parts of the scene may go out of view. So we see that there's a transformation that occurs as the person moves around and moves their point of observation through the environment. Yet again, more pictures, right? A lot of these pictures come from Gibson's book, not the previous slide, but these other ones do. So again, these are all meant to help us sort of visualize what the optic array is, this ambient light available at the point of observation, who for short, I guess, right? So here's another way to visualize it. So we're suggesting here that the information is to be found within the optic array. And what that also then entails is it entails that there is a need for us to analyze the optic array to describe exactly what those patterns are, right? And it's in these angles. So here I've got all of these lavender, I guess, lines converging from visible points. So it's meant to depict a person walking over like a grassy field, right? And all of these lavender lines are, again, the light sight lines, the ambient light converging to the person's point of observation. And these different lines have different angular relationships with each other. So it forms a pattern of angles. And the idea is that we're going to suggest that that pattern of angles, it's not homogeneous, right? Unlike the radiant light. Let me run back here real quick. Sorry. On the left here, the radiant light, all the angles are the same, right? And therefore it's homogeneous and it's not structured and there's no real pattern to all of that radiation. But on the right-hand side, we notice that the angles are not the same. And therefore, now there's a possible pattern or structure to the ambient light that was not found in the radiant light. So the reason I'm talking about this here is that we still need to find a way to formalize how we're going to talk about the pattern or the structure in the ambient light. And this is where this little blue circle comes in, right? So what we want to do is, this is really a challenge for geometry in a way, right? These are all angles, as I'm describing, visual angles, what we also sometimes call nested visual angles, because we just have objects, you know, all part of a visual scene, and that visual scene is typically very cluttered with lots of different things. And so therefore, there's a visual angle coming from one object. I can run back over here to our person in this room, right? And you can see that there's a visual angle. If you see my mouse maybe coming from the basically the top surface of this table, and that's going to project, or the proper word is subtend, a visual angle to that person's eye. There's also a portion of the wall between the far edge of the table and the bottom of this window that also is visible to that person, right? And that subtends a slightly different and smaller visual angle. And so then, of course, we have the entire window itself subtending a visual angle. So we have the portion of the wall is nested between the table and the window, right? And that's what I mean by these nested visual angles. So how can we describe these patterns? How can we visualize these patterns? This is where the blue circle comes in, because what we want to do is we want to imagine a situation where we can try to capture and depict and visualize the pattern of in the lavender lines without talking about retinal images. Because again, Gibson's trying to claim here that this information needs to be defined external to the observer and not defined purely in terms of what happens at the retinal surface. So what we're going to do is we're going to imagine, and this all this is, just an imaginary sphere. It's drawn here as a circle because it's hard to draw a sphere. But drawn here as a circle surrounding our observer. And we're going to let those sight lines, the lavender lines, intersect that blue sphere as they continue on their way towards the point of observation. And now we're going to try to imagine that where each one of those lines passes through the blue sphere, we could put a little dot there, a little pink dot, right? And now we want to think about what kind of pattern would that create if we were to put ourselves inside that sphere and imagine all of those little pink dots, right? So this is where we're going to start. Now try to think about that. Try to visualize this idea that if you what would that visual pattern look like if you're the person inside the imaginary sphere? And we're going to have all of these dots that represent visible textures. Well, we need to start a little bit here again with the environment. So Gibson also focuses on certain regularities in the environment. And one of the things that Gibson likes to talk about is the omnipresence of a ground plane, right? The ground, we are terrestrial animals, right? And the idea is that the presence of a level ground surface is always present in our visual world. And therefore that provides a sort of a background for everything that we look at. And the presence of that ground plane projects a specific kind of pattern to our to our visual system, to the point of observation, right, in terms of the ambient optic array. And that pattern is called a texture gradient. So what is a texture gradient? We need to think about that, for example. So let's look again. Now what I have done is I have kind of got our picture here again of our person, our stick figure person, walking over a grassy field. But what I did is that I also put these little black, tiny black lines here to represent blades of grass, right? And on a ground plane, the blades of grass are more or less spaced equally with each other. Maybe not literally so, but approximately so. We could say stochastically they are equally spaced with each other. It's much more true, of course, if we think about standing over a tile floor or a brick street. But regardless, we can think again that we're going to be standing on a surface of elements that are evenly spaced in the world, tiles on the floor, and perhaps a better example. But if we draw the sight lines, and that's where these lavender lines come back into the picture here. If we draw sight lines from every edge of every tile on the floor to our point of observation, one thing that we will note here is that the angular spacing is not equal. So even though the bricks themselves are equally spaced, or the tiles are equally spaced, the sight lines are not. And what you notice, of course, is that if we think about the angle, so let's look at the first angle right in front of our person's feet, our stick figure person's feet. The angle between the first and second intended to be a blade of grass here is large-ish, right? But between the second and third element, it gets a little bit smaller. Maybe hard to see that difference. But as we keep on going further and further away from our walking person, it becomes more obvious that the visual angle becomes smaller and smaller and smaller. And in fact, it does so at a very specific rate. And it's this compression of these angles, this ever narrowing of these visual angles, that's what we call the texture gradient, right? The gradient is the rate of change. And what we're looking at here is a rate of change in the size of those angles. And here, the claim is that the rate of change, or the gradient in these optical texture patterns or visual angles, is a function of the orientation of this surface. Now, what do I mean by orientation? Well, when you're standing on a flat ground, like a grassy field or a tile floor in your house, it's got an orientation that's level and flat, right? But if you were to think about what would happen if you were walking up a hill, like let's imagine now you're walking up a grassy hill, that ground plane now has a different slope and therefore a different orientation relative to you standing straight up. And therefore, you would end up with a different texture gradient because the ground is now oriented relative to you in a different way than when it is flat and level, right? Imagine if you're walking down a hill, you would even then have another different gradient. So this is the point here, is that there is a fixed one-to-one relationship at play, and that's the crucial theme. This is where we're going to start talking about, again, through geometry in this case, demonstrating the presence of information. And so the information is the texture gradient itself, the rate of change in these visual angles. And the state of affairs in the world that it corresponds to would be surface slant. So when you're standing on a flat level ground surface, you would experience one type of texture gradient. But if you're walking up a hill, you would experience a different texture gradient. If you're walking downhill, you would experience yet a different texture gradient. So the idea is that there's a one-to-one mapping, aka a unique mapping, between texture gradient and the slope or orientation of the surface that you're standing on. And this relationship between you and the ground that you're standing on is always specified by the visual textures, the gradients. That would be information. And it would therefore be informative and therefore useful for you to maybe understand how to walk on the surface, right? Here now, as I said before, we want to imagine that sphere surrounding the point of observation, and the sight lines are all converging to the point of observation, and we could put little dots on the sphere to imagine what the pattern would look like from if you were at that point of observation on the inside of the sphere. Well, that's what we're looking at here, right? Now we can see where that visualization comes in, because on the top left, we see a good example of a texture gradient that is a bunch of dots that in the real world would be equally spaced from each other, but in the visual pattern that we're looking at, which is what this would be, right? It's the visual pattern projected to that imaginary sphere surrounding the point of observation. It's not equally spaced. There's a gradient. There's an ever increasing or decreasing spacing or visual angle between them. The one on the bottom left seems to correspond more to a level surface. The one on the top left maybe is some sort of raising, slanted surface. The two on the right do not really feature a gradient whatsoever. So this is what happens when you were to take that surface and rotate it up so that it is completely perpendicular to the sight line. And this is exactly what would be happening if you were standing and facing a wall, right? So if you were standing and facing a tile wall, there's no gradient. And that would specify, of course, a surface that has essentially an infinite slope. And right, it's perpendicular to your sight line, and therefore it's a vertical surface. But when it's a horizontal surface, it would have a completely different gradient. Or if it's somewhere in between, right, slanted up or down, then again, you're going to have different gradients. Here we can see another variation of this theme, right? Here we're looking at texture gradients in terms of different kinds of angles, but what we see here is that on the ground surface or floor surface, right in front of, right at the bottom of the image, which would be kind of right where your feet would be if you were standing here, you have one kind of gradient, and then the gradient suddenly changes, right? And we see all the way in which those lines converge change very suddenly. And that sudden change in the gradient corresponds to a change in the slant. So there's another form of information available here that when this gradient is the same throughout a certain region of the scene, that would specify that the surface slant is the same. But when the gradient suddenly changes, that means the surface slant suddenly changes. And so what kind of situation in the world would create that? Well, a corner or a ramp or a hill would cause that kind of an effect. And that's exactly what this looks like, is a ramp or a hill or something like that, right? What about in this situation? As I just said, when the gradient is the same all throughout a particular part of the visual scene, that means the slant is the same. And what we're seeing here is, in fact, that this gradient is the same. I hope you see what I mean by that, right? When I say the gradient is the same all throughout this entire image, that's because the rate of change, the rate at which these lines converge and get closer together is the same. Now, obviously, there is a discontinuity in the center of this image, right? There is a sudden change, not in the gradient, as we saw here, but rather there is a sudden change in the spacing, the texture size or texture spacing, but without a change in the gradient. So this would correspond to something that looks like a step or a cliff, right? That's what this should look like to you. It should look like it would be like a step off or a cliff. And therefore, what we would say is that both the step above and the step down, it should be a step down since the spacing gets smaller, have the same slant because they have the same gradient, but one is raised up and closer to us and the other is down and further from us because of the decrease in the texture gradient, or not the gradient, but decrease in the texture size. Here are the same images side by side, so you can directly compare the idea that in one case, the gradient changes, and that corresponds to a change in the slant. In the other case, the gradient does not change, and therefore there's no apparent change in slant. There's only a change in the apparent depth, right? And that creates the cliff or step effect. Same pictures are there, but also on the bottom, we have other more complex ways that gradients can change in a way that you could see would specify all kinds of changes in slant. And those changes in slant then provide more complex information about some bumpy, wavy surface. So of course you can use changes in gradient and changes to get changes in slant, which actually provides information about shape, right? And the idea is that this can happen on the ground plane, but it can also happen on an object itself. And so the further claim could be that we're going to use texture gradients not just to perceive the shape and orientation of the ground, but we can potentially use texture gradients to perceive the shape of an object, and we can use that to recognize an object, which plays an important role in object recognition, right? Which of course is also useful. And then, of course, an important part of Gibson's theory is that when we look at objects themselves, not only do I just what I said was that they may have a texture gradient on their surface that specifies something about their shape, but objects themselves are placed on the ground plane, and therefore they are seen in relation to the texture on the ground plane. So when we look at this image, sometimes this is called an illusion, right? Because we might say, well, we got these three rectangular boxes here, the red one, the white one, and the green one. And I could ask a subject to say, well, are those things all the same size, or is one bigger? And a lot of times people might say, well, the green one looks bigger, right? And if you were to get out a ruler and measure these in terms of their two-dimensional size on the screen, you would find that they are, in fact, all the same size, right? And that's why it's treated as an illusion, because the green one looks bigger when it, in fact, is not bigger. It's, in fact, the same. But this is almost a trick question in a way, right? Because if I were to ask again, in the front of that question, are these the same size, or is one bigger or not? I'm asking in terms of their two-dimensional size, but when a person looks at this, they are thinking in terms of the three-dimensional interpretation of the image, or I don't want to say interpretation because maybe it's information, and it's just the three-dimensional perception of the image that occurs naturally because of the texture gradient found here. And the presence of that texture gradient specifies a depth relationship, and therefore the presence of that depth would naturally mean that the green box has to be in a three-dimensional world much larger than the white box, which would be larger than the red box, right? And so given the appropriate three-dimensional information of boxes laid out in a specific depth relative to the observer, yes, the green box is bigger. But if I want to be pedantic and try to force my research subject to judge only the two-dimensional size of the shapes, then I'm going to say, oops, fooled you, they're all the same size. But that's a trick, right? This is why Gibsonian researchers don't like to study illusions, because most of the time it's just a visual trick. If we were to eliminate all the texture gradients and just show those three boxes in isolation, people would correctly judge them as being the same size. But when we put them into this visual context of a three-dimensional seeing, that changes how people perceive the boxes, because it reveals that our visual system naturally uses that information from the scene, right? Here's again just another example. I like to just throw in more examples when I can. I don't want to linger over them, of texture gradients, objects that are all the same size and spacing in the world, but in terms of their optical texture, their optical pattern as projected to the point of observation, we see unequal sizing and spacing. Here's another example. This was more about changing surface slant on an object itself. It kind of creates this complex three-dimensional shape. Now, this is where I'm going to stop it. So let me wrap things up for this first video. So far, what we've defined is a way of detecting and describing patterns in the ambient optic array. And the primary thing we've talked about is this texture gradient that provides information about surface slant and object shape. One thing to keep in mind, as we saw in one of those previous images, is that the person shown in those rooms that goes from seated in the chair to standing up can move the point of observation to a new location, and therefore it transforms the optic array to a new optic array that might have new patterns. But one thing we also have to think about is that in the act of going from seated to standing, it's not about just having two different samples of the optic array, but it's about a continuous change. and the optic array. That is, you're going to experience visual motion. And there might, in fact, be a pattern in that visual motion, right? So it's not about just the pattern in the static optic array, but what happens when the optic array is now in motion because the person is standing up and is in the act of standing up, and that creates a continuous transformation in their visual optic array. Or when you're just walking around over the ground plane, right? So in the previous pictures, we think about just standing on the ground plane and you experience a particular optical texture. But what happens when you're walking, right? And what kind of continuous transformation is occurring? In this case, we're looking at a bird flying over a field, and there's again going to be an optic array pattern. But because the bird is not actually frozen in midair, but is really flying in continuous motion over the ground, there's going to be motion that occurs optically. And that optical motion is called optic flow. And so our next question is, are there, beyond the texture gradients in the optic array, are there additional patterns in optic flow that are also meaningful? What are they? What do they mean? And how can we demonstrate that people use them to perceive and control their actions in the world? But that's for next time. That's just a preview.